In section 5.6, we're going to talk about modeling harmonic motion. Periodic behavior that repeats itself over and over again, is common in nature. Some of the most familiar things to you that model harmonic motion are sound waves, light waves, alternating current, pulsating stars, the rise and fall of the tides, the rising and setting of the sun, certain animal populations increase and decrease over time. We call that the predator-prey model. In physics, you've probably also seen harmonic motion represented by a spring going up and down. We're going to talk about several different types of motion, starting with simple harmonic motion. For simple harmonic motion, we're going to use one of two formulas. We're going to use y equals a sine omega t or y equals a cosine omega t. The difference between these two equations is really where it starts. So at time t equals 0, if we say that something starts at its equilibrium point, we would normally say, that would be a sine function, as opposed to something starting at a maximum or a minimum displacement, we would use a cosine function. In both of these equations, A represents the amplitude. Remember that it's a square root, not a square root, an absolute value, because the amplitude is a distance above and below some equilibrium point. For this, it's really just the maximum displacement of the object. The period is going to be 2 pi over omega. The only difference is we're using omega instead of k. Just kind of depends on which section we're in, on what letters of the alphabet they use in these equations. The period is the time required to complete one cycle. But we're also going to talk about frequency. Frequency is just the reciprocal of period. So it's omega over 2 pi. It's the number of cycles per unit of time. In example 1, let's look at the example of a vibrating spring. You've probably talked about a spring in physics class. You know, you hang a spring here, you might stick a weight on it. So you pull the spring down, and what does it do? It's got this harmonic motion. It goes up, it goes down, it goes up, it goes down. Equilibrium is where the spring lays when it's not in motion. So the displacement of a mass suspended by a spring is modeled by the function y equals 10 sine of 4 pi t, where y is measured in inches and t in seconds. Find the amplitude, period, and frequency of the motion of the motion of the mass, and then sketch a graph of the displacement of the mass. Well, for part A, amplitude's easy. The amplitude is 10, and it's 10 inches. That means that the spring goes as high as 10 inches above equilibrium and as low as 10 inches below. The period is going to be 2 pi over omega. Well, in this case, omega is 4 pi. When I reduce that, the pi's cancel and I'm left with 1/2. And the period is a time, so it's in seconds. And then the frequency is just the reciprocal of the period. So the frequency must be 2, and it's in cycles per second. The second part of the problem asks us to graph this. Well, if we're just going to do a general sketch by hand using this information, I'm going to do my graph. The period is 2 seconds. So I'm going to make 2 my furthest point. So the way I have you graphing is having this in fourths. So if 2 is the distance to my 1 period, then this is going to be 1. Actually, I should go back because my period isn't 2. My period is 1/2. Sorry about that. So half of that is 1/4. So this is 1/8. and this is 3/8. So we can graph our 1 period of this cycle. And then my maximum displacement is 10, so it goes as high as 10 and as low as -10. We'll call equilibrium 0. So since this is a sine graph, my sine graph starts and ends on the x-axis, or the midline. In the middle, it will also hit the midline. Between the first two x-intercepts, it will hit its maximum, and between the next two, it will hit its minimum. So this is the graph of 1 period of this spring cycle. In problem 2, it says a tuba player plays the note E and sustains the sound for some time. For a pure E, the variation in pressure from normal air pressure is given by the equation V of t is equal to 0.2 sine of 80 pi t, where V is measured in pounds per square inch and t is measured in seconds. Find the amplitude, period, and frequency of V. Well, the amplitude is always the absolute value of the number being multiplied in front of the sine or cosine function. So in this case, the amplitude is 0.2. The period is 2 pi over k, and in this case, k is 80 pi. So I'm going to reduce that fraction. The pi's cancel, and 2 over 80 is 1 over 40. And the frequency is just 1 over the period, so it must be 40 over 1. Now let's sketch a graph of V. Now, if you look at the problem in the textbook, they sketch many periods of this function, but we like to sketch 1 period of the function. So we're going to draw something very basic. So there's no vertical shift, there's no horizontal shift. So we just need to worry about the amplitude and the period. So the amplitude is 0.2. So it goes up to 0.2. It goes down to -0.2. The period is 1 over 40. So I need the tick marks in between 0 and 1 over 40. So there are technically 5 tick marks, even though we're only going to draw 3 more. Halfway between 0 and 1/40 is 1/80. Halfway between 0 and 1/80 is 1 over 160. And halfway between 1 over 80 and 1 over 40 is going to be 3 over 360, because, or which is, it's 1 over 120, I guess I should have written it reduced. Because when you make these tick marks, if the first one is 1 over 160, then the next one is 2 over 160, the next one is 3 over 160, and the next one is 4 over 160. But we do need to reduce them. Since it is a sine curve that has not been reflected over the x-axis, the sine curve starts and ends on the midline. The point in the middle also on the midline. Between the first 2 midline points is the maximum, and between the next 2 is the minimum. So that would be 1 period of V. Sound is an important simple harmonic motion. It's produced by the regular variation in air pressure from the normal pressure. If the pressure varies in simple harmonic motion, then a pure sound is produced. The tone of the sound depends on the frequency, and the loudness depends on the amplitude. So if I say, if the tuba player increases the loudness of the note, how does the equation for V change? Well, it's going to change the amplitude. So if you increase the loudness, you should increase the amplitude. So if the tuba player is playing a note incorrectly and is a little flat, how does the equation for V change? Well, if the note's flat, that's going to change the tone, which means it's going to change the frequency. So if it's being played incorrectly and it's a little flat, then it's probably going to decrease the frequency. A mass is suspended from a spring. The spring is compressed a distance of 4 centimeters and then released. It is observed that the mass returns to the compressed position after 1/3 second. Find a function that models the displacement of the mass. All right, so first of all, you kind of have to have an idea of what the picture of this looks like, and hopefully you did this in physics. So you have this spring with a mass on it, and we'll say this is what the spring with the mass looks like in rest position. So if we compress it 4 centimeters, that means we're going to move it up 4 centimeters. And so it kind of makes the spring a little tighter. So we're going to start here, and then we're going to let it go, and then it's going to go down and up and down and up, and then eventually friction kind of hits, and then eventually it'll slow down and stop, but we're not going to worry about that for this particular problem. The first thing I have to determine is, am I going to use a sine function or a cosine function to represent this situation? So you have to think about where the graph starts. If a graph starts at its point of equilibrium, we use a sine function. But if the graph starts at a maximum or minimum value, we would use a cosine function. Well, since we're compressing the spring to 4 centimeters, we're going to use a cosine function. So y is equal to a cosine of kt. The reason we're going to use t instead of k is because the spring is oscillating for a particular amount of time. All right, so the amplitude is going to be 4 since that's where I start, and I'm starting up 4, so it's going to be positive. Now I need to figure out what k is going to be. Well, remember that k comes from the period. It's 2 pi over k, and they told me the period is 1/3. I'm going to set 2 pi over k equal to 1/3, and I'm going to solve that proportion. So k is equal to 6 pi. So y equals 4 cosine of 6 pi t would be the equation that represents this situation. Then, to sketch a graph of the displacement of the mass, so we're going to do something very basic. Remember we said we know the amplitude is 4, so it must go up to 4 down to -4. The period is 1/3, so half of 1/3 is 1/6, and half of 1/6 is 1/12, so that's 1/12. 1/6 is 2/12. The next one would be 3/12, which is 1/4. Since it is cosine graph, it's going to start and end its period at the maximum. In the middle, it'll hit its minimum. In between those, it'll hit the midline. And so one period of the graph looks like this. Remember that when we are graphing or writing trigonometric equations, that we can use input variables for whatever best represents the problem at hand. The textbook likes to use the equation y equals a sine or cosine omega t minus c plus b for graphs that have been their amplitude's been changed, their period's been changed, they have a phase shift and a vertical shift. I'm used to using y equals a sine or cosine k of x minus c plus b. Either way, it doesn't matter. Omega, k, when you're finding the period is 2 pi over k, or 2 pi over omega, just so you know that they're really doing the same thing here. They're just switching up variables on you to confuse you. So let's try to create an equation that encompasses all these different transformations. In example 4, a variable star is one whose brightness increases and decreases. For the variable star delta Cephei, I'm not sure if that's how it's pronounced, but we'll go with it. The time between periods of maximum brightness is 5.4 days. That's the period. Or that's going to help us determine the period. Well, it is the period. We're going to use it to find k. The average brightness or magnitude of the star is 4.0. This is the baseline or the midline or the line of equilibrium. That means the graph has been shifted up 4 units. And its brightness varies by plus or minus 0.35 magnitude. Pretty easy to figure out. That must be the amplitude if it varies by plus or minus. Find a function that models the brightness of delta Cephei as a function of time. All right, so in order to write this equation, the first thing I have to determine is, am I going to write a sine equation or a cosine equation? Well, since it says that the time between periods of maximum brightness is 5.4 days, that means the graph must do this, and therefore it's going to be cosine. Next, I know that we're going to have an amplitude that's going to be 0.35. The graph is going to start with positive 0.35 because it tells me in the problem that it starts at its maximum. And then we're going to do cosine. Well, I shouldn't, skip that. So, erase that. Y is equal to 0.35 cosine of, now let's find K. To find K, 2 pi over K is going to equal the period. So K is going to equal 2 pi over 5.4, which is approximately 1.164. So now I'm going to have 1.164. They want us to use t because it said it varies as a function of time, so t. We'll worry about this in a second. And then we just said that because the average brightness is 4, that's your midline, so the graph has been moved up 4. All right, so here's the thing. How do we know what C is? Well, if we take the time t equals 0, be a time when the star is at its maximum brightness, then there's going to be no horizontal shift. So we're going to say C is equal to 0 because a cosine curve achieves its maximum at t equals 0. So we actually can skip this part and just kind of make this 1.164t plus 4. And this would be the equation that represents this particular function. Now let's talk about the graph. To sketch the graph, we said that the line of equilibrium, the midline, is at 4. 1, 2, 3, 4. I like to draw a dashed line here to remind myself of where I'm oscillating about. Now, the amplitude is 0.35, so I probably have to do a little bit different scaling on my y-axis. So maybe I'll get rid of these. So if it oscillates 0.35, that means the highest it's going to go is 4.35. That's going to be its maximum. And its minimum is going to be 4 minus 0.35, which is going to be 3.65. 1 period is going to be 5.4 days. So I need 3 more tick marks because the beginning one is going to be 0. So half of 5.4 is 2.7. Half of 2.7 is 1.35. And then halfway between 2.7 and 5.4 is going to be 4.05. So I've labeled my tick marks. It's a cosine curve. Cosine curves start and end their period at their maximum. Halfway in the middle they hit their minimum, and in between the max and min they hit that midline. And there is 1 period of that graph. In order to do this next problem, there are some things you need to know. The number of hours of daylight varies throughout the course of a year. In the northern hemisphere, the longest day is June 21st and the shortest day is December 21st. These are things you probably already know. The average length of daylight is 12 hours, and the variation from this average depends on the latitude. For example, if you live in Fairbanks, Alaska, which is really far north, you experience more than 20 hours of daylight on the longest day and less than 4 hours on the shortest day. There's a graph in the textbook on page 416 that shows the number of hours of daylight at different times of the year for various latitudes. It's apparent from the graph that the variation in hours of daylight is simple harmonic motion. So, for our problem, in Philadelphia, which is at 40 degrees north latitude, the longest day of the year has 14 hours and 50 minutes of daylight, and the shortest day has 9 hours and 10 minutes of daylight. We want to first find a function L that models the length of daylight as a function of t, the number of days from January 1st. Okay, so the first thing we need to do is, if you look at the graph on page 416, you'll see that our midline appears to be, oops, I don't want to move that. Our midline appears to be here. So we're going to say that our vertical shift is 12. Now, I also want you to notice the shape of the graph. I want you to notice that over here it seems to start on the vertical shift and it ends on the vertical shift. We're going to use a sine function to best represent this. Well, now I need to do a couple other things. So one of the things I got to do is find the amplitude. Well, they told me that the longest day of the year was 14 hours and 50 minutes and the shortest day was 9 hours and 10 minutes. I can find the amplitude by subtracting those two values and dividing by 2. So another formula for finding the amplitude of a function is max minus min divided by 2. Now, you have to have one unit of measurement. You can't be in 14 hours and 50 minutes. You either have to be all in hours or all in minutes. And for our purposes, it's probably better if we're just all in hours. So 14 hours, 50 minutes is 14 and 50 over 60 minutes. And 9 hours, 10 minutes is 9 and 10 over 60. If you want to turn those into decimals, just turn 50 over 60 into a decimal and you'll get approximately 0.83 repeating. So we're going to say this is 14.83. And then 10 over 60 is 0.17 because 0.16 repeating. So this is 9.17. So when I take those two values and I subtract them and I divide by 2, I'm going to find out that the amplitude is approximately 2.83 hours. That means that the number of hours of daylight vary 2.83 hours more than 12 and 2.83 hours less than 12. All right, now let's go find our K or omega depending on which equation you want to use. So y is equal to a sine, I like to use k, t minus c plus b. So there are things I know about this equation, like I know that b is going to be 12. I now know that a is going to be 2.83. Now, is it going to be positive or negative 2.83? Well, if you look at this graph, it starts at the midline and it goes up from there. That's your traditional sine curve, which means that it's going to be plus. To find k, I need to know the period. Well, we're talking about the number of daylight hours in a year. The period is 365 days. So to find k, we're going to do 2 pi over k is going to equal 365. That means k is equal to 2 pi over 365, which is approximately 0.0172. So now I'm going to take this out, and I'm going to put 0.0172. The last question, or last part of this problem is there a phase shift? Well, since the average length of daylight is 12 hours, and the graph is shifted up by 12, the average value of 12 hours occurs twice during the year. Well, the first time that happens, the spring equinox, that's why we call it the spring equinox, is on March 21st. Well, that's going to be 80 days into the year. So that means that C is going to be 80. Move this up a little. So the spring equinox occurs on March 21st. That's when there is the same number of day and night hours in the 24-hour period. And this happens on the 80th day of the year. So we're going to say C is 80. So now I'm just going to go here. I'm going to take that out, and I'll put 80 in its place. And look, I've got a nice little equation. In part B, an astronomer needs at least 11 hours of darkness for a long exposure astronomical photograph. On what days of the year are such long exposures possible? Well, our equation is not about the number of hours of darkness, it's about the number of hours of daylight. So, if you need 11 hours of darkness, you need 13 hours of daylight. So what I'm going to do is I'm going to graph in my calculator my function, and in y2 I'm going to graph y equals 13 and determine where the two lines intersect. Here's what my graph looks like if I use the following window. The reason for this window is that my period is 365, so I went from 0 to 365. Since my midline is at 13, or not my midline, I want to find out when I'm going to be at 13 hours of exposure. I need to go a little bit above 13, a little bit below 13, so I made my y min 10 and my y max 15. There's no hard and fast rule that says those are what you need to use. That's just what I use. Now I'm going to find the points of intersection of these two graphs. I'm going to find out that this point of intersection is at about 101 days. And I'm going to find out this point of intersection is about at 242 days. Well, now I got to figure out where exactly those lie in the number of days per year. Well, you need to know things like January has 31 days, March has 30, February has 28, March has 31, April has 30, May has 31, June has 30, July and August both have 31. September has 30. October has 31. November has 30. And December has 31. If you know that, then you can figure out approximately what day these occur on. So this occurs on April 11th. And this one occurs on August 30th.